So in this section, what we're going to do is we're going to try and draw together some of the concepts that we've been looking at in the preceding sections. So we're going to try and make it a little bit more concrete what we mean by a logical address, what we mean by a physical address. I'm going to try to show how there is a mechanism for mapping the logical address to the physical address. So we're going to try and flesh out with a little bit more detail the mechanism and the translation, the mapping that takes place between the logical address and the physical address. So I'm working with a little bit of software here that's not a standard PDF, display software. It's going to allow me to annotate this. So at the moment you can see that I'm looking at, on slide 21, a diagram. So the diagram shows us some rather obvious and recognizable components in a computer system. So for example, we can see here the CPU, we're well used to that. We can see that there's a process which is executing, and that is process P7. We can see also as well that process P7 is executing a machine code instruction which is LOD 101. So obviously there are two components to this. The first component, number one, is the actual machine code instruction itself, and the second component is the address. So you remember that when we were talking about this in Chaos 1, we talked about the operator and then we talked about the operand. So the operand here is an instance of a logical address. My handwriting's appalling, I apologise for that. So what we can see is that P7 is executing the machine code instruction LOD 101. Now what we can also see as well is that the address space that is occupied by P7 is this address space over here. So here's P7, it's been loaded into main memory by the kernel as part of its transformation from being a program into a process, and we can see that it occupies the address range 300 through to 500. So these addresses that I'm highlighting here, they are physical addresses. Okay, so they are actual RAM addresses. They're addresses that exist in the circuitry of the main memory. So when P7 executes the machine instruction LOD 101, this number here cannot refer to a physical address, because if we allow it to reference a physical address, then we're saying that it can reference this address down here, which is the physical address 101. And the problem with that, very obviously, is that this physical address 101 is inside the kernel's address space. So we remind ourselves that the kernel is privileged and that it is in control of all the hardware and all the software in the system, including all of the executing processes. So this would be an unforgivable violation of security, protection, isolation, all of the desirable goals that we talked about earlier on when we were thinking about memory management. So this is not allowed and it has to be prevented. So the question then is, how do we take this 101, which is our logical address, and translate it into a correct physical address? So we're assuming that 101 will map to an address which is somewhere in this address space here. In other words, the address space that's been allocated in physical memory to P7. So the question of how we do that is done by using another bit of circuitry called the memory management unit. So you can see that the logical position of the memory management unit is that it sits in between the CPU and the main memory, and it takes as an input a logical address, and then it produces as an output a translated, mapped, converted physical address. So logical addresses go into the memory management unit and physical addresses come out. So the question then is, well, what is being done inside the memory management unit to accommodate this, to do this translation? And basically, for this very simple example, which is demonstrating the idea of relocation, we can see that internal to the memory management unit, there is a special register, which is called the Relocation Register. So the Relocation Register is set to a value, which is the first physical address belonging to the process in main memory. So we can see that when P7 was loaded into this portion of main memory, its first address, its first physical address is 300, and its last address would be 499. So some of these figures are a little bit arbitrary, but you get the general idea. So another way of expressing that is to say that the total portion of allocated address space in RAM for P7 is 200 bytes. Okay, so these are the physical address space for P7, and the logical address space is inside that address space. So when the machine code instruction LOD 101 is executed with the logical address 101, what actually has to be executed in terms of the circuitry, in terms of the hardware, is LOD 401. So the question then is, how do we do this? Well, the relocation register, as I've just said, is set to 300, which is the first address, and all we do is we take the logical address, which is 101, and we add the two together like so, and this gives us our 401, which is the correct physical address. So now if you think about, well, where would 401 be? Well, 401 would be just about here. As a physical address it would be 401, but as a logical address it would be 101. So this is pretty neat. It means that the process can reference its own internal address space, and then the memory management unit takes care of the low-level mechanics of translating that logical address into a correct physical address. Naturally, the entire memory management unit, the values that are set into the registers for the relocation register, they're all under the control of the kernel. Okay, so this is a very nice example because it shows us relocation. So let's proceed on to the next slide, and the next slide shows us the same diagram. So you can see that we have the same set of processes loaded into main memory. So there they are there. There's three processes plus the kernel. There's the kernel. There's P7 that we were looking at a moment ago. There's P22 and there's P12. They are all allocated a portion of the physical address space. So the kernel is from 0 through to 299. P7 is from 300 through to 499. P22 is from 500 through to 699, and P12 is from 700 through to 900. Okay, so the layer of the diagram is pretty much the same as before. There's our MMU as before, and there's our CPU, and there's our process, except this time a process that is executing is not P7 but is P22. So remember that when we think about memory management, we always think about it in terms of a multitasking system. So recall that in a multitasking system there are always multiple processes that are available, ready to execute, and just waiting for the chance to get onto the CPU. So we can imagine in this example that P7 was executing for a period of time, and then it was descheduled from the CPU, and P22 was picked from the ready pool and then scheduled into the CPU. So we imagine now that P22 is executing, and we can see that it is now executing the machine code instruction LOD 101. And as before, we can see that there are two components to this. We can see that there is, first of all, the operator, which is load direct, and then we have the operand, which is the logical address that is being executed by process 22. Now we know that this number here, 101, cannot be the physical address, because if it was, we'd be accessing an address down here, and that's not correct. We're not allowed to access the address space of the kernel, so we know that it has to be translated into a physical address space. So we can see that the MMU, as before, is responsible for taking the logical address space and converting it into the logical address and converting it into a physical address. So it does this in the same way as before. There is inside the memory management unit the relocation register, but the relocation register in this instance has a new value which is 500. So that 500 refers to the starting address of the address space that belongs to P22, and then to convert the logical address 101 into the correct physical address, it has to be added to the starting address of P22. So that gives us the new physical address, which is 601, which would be roughly about here. So its physical value is 601, but its logical value is 101. The process, P22, doesn't even know that this is taking place because it is hidden from it. It's only ever able to see its logical addresses. So the memory management unit is something that is essentially invisible to a process like P22 or P7, and importantly, it is under the control of the kernel. So the question then is, who set this value here? And the answer is that the kernel is the entity responsible for controlling the value of the relocation register. And of course, this relocation register, the machine code instructions to change the value of that relocation register, they would be privileged. Okay, so we'll do another example just to illustrate the translation of logical addresses into physical addresses. So we can see that in this instance we have again same components, CPU, MMU, main memory down here, and you can see that we have a process P12 which is executing, so it's been scheduled onto the CPU. It is executing the machine code instruction LOD 101. As before, we have the operator load direct 101. The operator is LOD, and then the operand is the logical address 101. So this is of course internal to P12. What it means is an address roughly about here, not down here. Okay, so this is completely wrong down here. If we end up accessing the kernel's address space, well, that's forbidden. That's a major security violation, so we wouldn't be allowed to do that. Okay, so when we execute this machine code instruction, the operand part, the logical address 101, gets sent to the MMU. As before, the MMU has been reset. Its relocation register is now set to 700, which is this starting address here, which is the beginning of the address space, the physical address space allocated to P12. And then as before, we take the logical address 101, we add it to the starting address 700, and that gives us the new physical address, which is 801, which is about here. So there's the physical address 801, and the logical address is 101. So most importantly, the process only ever sees the logical address 101. The translation of the logical address into the correct physical address is taken care of by the MMU, working under the control, as ever, of the kernel. So I suppose this raises a number of different questions. We still have an issue or a problem, which is how do we allow programs to grow if their memory requirements change? And then another question is who puts the programs P7, P22, P12 into these segments of main memory? Could, for example, P7 be located in the portion of main memory where P12 is? Could P12 sit where P22 is? Could P22 sit where P7 is? And of course, if you think about that, then the answer is yes, they must be able to move about in main memory, because if they weren't, then we would essentially be saying that P7 could only ever exist in the range of addresses from 300 through to 500. Well, that's nuts. That wouldn't be an effective use of main memory. So we'll come on to that later on as a teaching point, but for the moment, the main takeaway is the idea that logical addresses get translated into correct physical addresses by the work of the memory management unit. The key thing here is the principle of relocation, that we are translating the logical address into a correct physical address through a very simple arithmetical mapping, and that this arithmetical mapping has two benefits. It allows us to firstly to be able to move programs about in the physical address space wherever they may be, and always have their logical addresses correctly reference that program's address space. And also as well, it shows us a pathway perhaps later on to how we might actually implement a more efficient memory management scheme. So, in conclusion, the user process, P7, P22, P12, never sees the physical addresses. The user process only deals with logical addresses, and all the hard work is carried out by the memory management unit, which converts the logical addresses into real physical addresses by adding the relocation register to the logical address.